Good morning, everyone. Good afternoon for you, most of you in Chengdu right now. It is a pleasure to have this opportunity to talk to you again. It is a pity that I could not join you there, and I hope that the present limitations due to COVID confinement are not too harsh for you. We heard in the news here that it was again a bit closed your city, but I hope it's not too bad. I see you are in office, so that means it's okay. All right, so I must start first thanking Wei Ming Liu and all the students in your team present for this conference, and all the professors at the Chinese Academy of Science. And I want to thank again this opportunity within the framework of the President's International Fellowship Initiative. In this talk, I will present a review of what is known up to today, to present day, about the causes for the largest environmental change in the last 65 million years, since the beginning of the tertiary. And I will try to summarize what we think are the mechanisms responsible for this major environmental change that turned the Mediterranean Sea into a huge salt pan accumulating kilometers of thickness of halite in the bottom of the ocean. Just to put in scale the size of the problem that I will address here, this would be the area of the Earth continents that became endorreic at the end of the Messinian times. The green line is depicting approximately the drainage basin of the Mediterranean, and including these Asian endorreic basins today. And this area accounts for about 15% of the continental land surface today. And all that area was not contributing to the geochemical evolution of the ocean for about 600,000 years, because it was isolated. There was no connection, or mostly no connection to the rest of the ocean. So, and at the same time that this huge area was not contributing to the ocean was losing about 6% of the dissolved salt in the global ocean that became trapped and precipitated in these lakes, or this Mediterranean Sea that became a system of lakes, and were accumulating all these 1 million cubic kilometers of salt. Just to remind what is the geodynamic context of the formation of the Mediterranean, you remember that the Tethys Ocean was consumed by subduction due to the convergence between Gondwana and Laurasia after the Pangaea's breakup. And this subduction eventually led to a situation similar to today, where these different slabs are present today, visible in seismic tomography, and the retreat of these dense pieces of lithospheric, oceanic lithospheric slabs are producing back arc extension in several places of the Mediterranean, most remarkably in the Tyrrhenian Sea. And also, as you can see in this map of the seafloor age, you have this Neogene back arc extension in the Western Mediterranean. And this is in contrast to the very old ages of the lithosphere that have been derived for the eastern part of the Mediterranean. This is in fact some of the oldest pieces of oceanic lithosphere that is left from this Neo-Tethyan subduction underneath Eurasia. And so it has never been drilled, this oceanic lithosphere, but it lays here underneath the thickest packages of halite in the eastern part of the basin. This is a depiction of what the distribution of salt in the Mediterranean is. In red you have halite, in green carbonates and sulfates, and this is the typical distribution referred to as the bullseye distribution of Messinian salt, meaning that the carbonates and the sulfates are more laterally extended towards the margins of the basin than the halite, which is reduced, confined to in the deepest areas of these different subbasins of the Mediterranean area. To understand this, let me remind what is the sequence of salt precipitation. Let me see if everything is working okay. Cool. This would be the sequence of halite precipitation. First, when you evaporate seawater, normally you would first precipitate calcite and dolomite, and then when you have evaporated down to 20%, 19% of the volume is left in your evaporating brine, then you start precipitating sulfate, calcium sulfate, for example, gypsum and anhydrite. And halite takes at least 90% of evaporation to happen, leaving only 10% of the brine. It is at that point that halite is precipitating, and finally you get the potash and salts, the bitter salts, which are well known for their importance as fertilizers, and these they need to evaporate more than 96% of the brine before you can get them precipitated. And as a result of this sequence, what you would obtain in a column of precipitation, if you reach enough saturation, you would have a small layer of carbonates. On top of that, you would get gypsum, then halite, which accounts for most of the salt precipitation, and finally the potash salts. And as a result, you would get a distribution like this, because since the water level is decreasing as this column of halite is accumulating, then you get the first salts laterally more extended than the later ones. And that would be responsible for this bullseye distribution that I was talking about. This is again the similar image. You have the halite layer here in this yellowish green color, and this yellow here, and you see the gypsum laterally more extended. One thing important to highlight is that actually the stratigraphy is very different in the western and the eastern basin, whereas in the eastern side you have mostly largely pure halite accumulated at very large thicknesses, above 1.5, 2, and even 3 in places, 3 kilometers in thickness. In the western basin, you have this sequence known as the trilogy, where with 3 very distinct units, the lower evaporates the mobile unit, which corresponds to halite, and the upper unit. And this has never been drilled, unfortunately. So we know what the upper unit is. It includes evaporites, resedimented evaporites, and we know the halite because of the very distinct seismic phases. We know it's halite. It forms diapirs that I will show later, but we have no much idea what the lower unit really is. A good part of what I just showed is actually known already since the 60s, and this was the time when Raimondo Selli from University of Bologna was actually defining crisis, the salinity crisis itself. And in fact, the Messinian stratotype was defined already in the 19th century by Karl Mayer. And by correlating the presence of all these evaporites in outcrops in the continental margins. Outcrops like this one, this is from southern Spain in Sorbas. All that what you see in this picture is largely pure gypsum, primary gypsum crystals. And there is actually a cave where you can go and see the crystallization patterns very well, and you can see where the nucleation takes place. So this is the base of this gypsum. The clastics underneath this have been removed by underground erosion. And here you can see, really, you can touch the initiation of the nucleation of gypsum crystals very well. So this nucleation grows in these beautiful patterns, radial patterns, laterally upon when saturation for gypsum is reached at 140 grams per liter. As for salt, you can only see it because it dissolves very fast and very easily. You can see it best in this salt mine in Sicily, where it is exploited. This mine is actually feeding halite to most of Europe, and the size of this exploitation is really impressive. And one interesting thing that you can see there is that there is this layering, these varps, these annual layers of cyclicity, each of them corresponding to a year, and this gives an idea what is the rate of accumulation of this sediment, of this salt. This 150 meters per kilo year, this means that in just a few tens of thousands of years, you could account for even the thickest salt deposits in the Mediterranean. So this is giving an indication that actually this halite precipitation might have been really very fast, in that order of tens of thousands of years. This is the tectonic context where this mine is set. This is the Caltanissetta basin in Sicily. And as you can see, the halite body is trapped within reworked lower gypsum. And this, even if this is topographically lower, stratigraphically it has been derived to be higher than the source of this reworked lower gypsum. So this is stratigraphically higher than the primary lower gypsum. It comes later in time. So the idea is that these blocks of primary lower gypsum, they are falling into topographically lower areas, and then the halite is simultaneously or coevally accumulating in the deeper parts of these basins. The halite has been known, as I said, even from seismic surveys. It has been observed in the Mediterranean basins for a long time, because these deposits are very recognizable because of the formation of diapirs and because of the peculiar, the rapid seismic velocity. But it was in the late 60s and early 70s that the first drillings of these evaporites were produced during the DSDP campaigns by these three researchers, Bill Ryan, Kenneth Su, and Maria Bianca Chita. And thanks to those drillings, very interesting samples were obtained, showing, for instance, this nodular anhydrite that was interpreted as proof for exposure and high temperature Sapka-like environments, evaporitic environments, meaning that the layer of water where these evaporites were deposited was very shallow. And this is interesting because actually these drillings, the seafloor today is at minus 2.6 kilometers, so it's very deep in the ocean, and that would give an indication, unless there is some other way to explain that the water layer was removed, was evaporated, and the seafloor at the time was exposed or nearly exposed to the air, to the atmosphere. In the right, you see this halite core showing what was interpreted as cracks filled with halite, and this was interpreted as desiccation cracks formed typically in salt pans. So again, supporting the idea that this deep seafloor had been exposed to the open air. As I said, the lower units of the Western Mediterranean have not yet been drilled. In spite, we tried to propose two drilling initiatives named DREAM and DEMISE. Unfortunately, none of them has yet been approved. It's a very complicated process, but there are some recent commercial drillings, not recent, but they have been recently released for scientific purposes that give, for the first time, a glance into how the sedimentation in the Eastern Mediterranean starts. And it would be really interesting to manage to have the same for the Western Basin to complete the picture at the Mediterranean scale. So out of all this, there is this stratigraphy that is kind of more accepted among a wide community of researchers. And the vision, the general view, we can summarize by splitting the events into deep basins and marginal basins. And the idea is that both areas, margins and deep abyssal areas of the Mediterranean, behave differently through time because they are differently affected by the sea level changes related to the Messinian crisis. The idea is that the first stage is when the primary lower gypsum is accumulated in the marginal areas, and then after this comes the halite accumulation, some erosional surfaces that are contested. Not everyone agrees when does this erosion and subaerial exposure happen. This would be the time when erosion of the margins is also taking place. And then the upper gypsum and the lagomare take over. The lagomare is a very characteristic unit that suddenly receives fauna from the Paratetian lakes, so these lake systems that were in the eastern side of the Mediterranean, in what today would be the Caspian Sea and the Black Sea, and suddenly all this fauna appears in the Mediterranean sedimentary record, and then this history ends at the base of the Pliocene with a very sharp and sudden change to normal open marine conditions. But this is a little bit what must be explained. So I showed evidence about the salt deposits, and I will now show other evidence fundamental to the Messinian salinity crisis, which is related to erosion and the biological impact, and then I will talk about mechanisms. So another aspect about the Messinian salinity crisis that is relevant is the the erosion of the margins. And many of the streams, like the Po River, the Rhone, Ebro, and the Nile River, they are showing erosional features, suggesting that this erosion of the margins might have been enhanced due to lowering or drawdown of the level of the Mediterranean basin. Note that in order to accumulate the salt that we've been talking about, you don't actually need to expose the seafloor. You don't need to lower the sea level below the present level, but you just need to close the outflow at the connection with the rest of the global ocean, the same as in a salt pan. So the fact that suggests that there is actually a lowering of the sea level is what you see in this figure, is these erosional features that I will show now. One of them is, for instance, this Sahabi gorge in the Sirte Basin. This is onshore Libya, and this is covered today in sand, so you cannot see this. This is known through geophysical methods, but it seems like there is a river incising and that was draining to the Mediterranean at the Sirte Basin in Libya, and this incision has been covered and is not visible anymore. Today, this river does not exist anymore, but it has been argued that maybe the source for this water was the Chad Lake in Central Africa. Another very well-known incision attributed to the Messinian lowering in base level, in Mediterranean level of the sea, is the Nile Canyon. This is an old imaging from the first times that this idea was proposed. But there is more modern data, like this one in the offshore the Ebro Delta. This is eastern Spain, and you can see the present Ebro Delta. If you strip in this 3D seismic cube, you strip the plioquaternary layer, then what you obtain is a very rough topography, very suggestive for subaerial exposure and river dendritic network incision into this pre-existing delta sediment. So, and then this is again, as the sea level rises again to the normal position, then the aggradation of this deltaic body continues and covers these incision patterns. And actually, there is some work done on those data that highlight not just dendritic patterns, but also meandering shapes and even river-like terraces, very suggestive for subaerial river being responsible for all these patterns. And the other aspect that must be linked here is the biological impact. In the continents, there has been this time gap in the diversification of plants, leaving this space around the Messinian salinity crisis, where plant, perhaps or purportedly due to the impact of the Messinian crisis in climate, plants stop diversifying at the speed they used to before and at the speed they did after. Better known is the impact on mammal migrations, and it has been suggested that the lowering of this of the Mediterranean level allowed big and large mammals to migrate from Africa, between Africa and Europe, and also, as I show in this case, also between Iberia and the Balearic Islands. So there is species like capri and many others documented in across the Mediterranean. But of course, mammal migration is always arguable because these migrations can also happen without significant sea level changes or actual breaches in the land. Can randomly happen by other means that not just subaerial exposure. Perhaps the hope in understanding the biological impact of the Messinian salinity crisis and have independent constraints from biology that can show us something about the crisis comes from the marine record. And there is this ongoing work by Constantina Aghiadi that is based on assembling the marine fossil records. It's a huge effort involving a lot of paleontologists and more than 20,000 occurrences of species all across the Mediterranean in more than 850 localities. And the preliminary results from these are very promising because they show that actually the richness in species is affecting the Mediterranean, is reducing the richness of species in the Mediterranean already before the Messinian salinity crisis gap. And also it's showing that the similarity, this is the difference between the Tectonic and the Messinian marine biological record is smaller than between the Messinian and the Zanclean. So this is suggesting, this jump here in the similarity is suggesting that something happens in between, something happens during the Messinian that actually makes the later, the Zanclean, the Pliocene biological, the marine population very distinct from everything that happened before. And actually one of the interesting results also, I insist, this is preliminary work, but a very interesting result also from this work seems to point to the east to west gradient in species richness that is observed today in the Mediterranean. So this increase in species richness from east to the west, this seems to actually initiate after the Messinian salinity crisis. So with the input of Atlantic new species into the Mediterranean and the reset of the entire ecosystems. So in this summary of data, I just I've been very fast, of course, but there are many open questions. I hope I was giving this impression that there is many open doors that must be better understood from the climatic, biological, and sedimentary point of view. But the open question I will focus on in the next part of this presentation is on what are actually the mechanisms that controlled this evolution of the Mediterranean and are responsible for these observations from a mechanistic point of view. All right, the causes for the Messinian salinity crisis, the first most obvious thing to state is that what is causing the today's salinity in the Mediterranean, which is slightly above the global average, is the responsible for this is obviously the relative disconnection in the Strait of Gibraltar, or the small connectivity with the rest of the ocean. And this, together with the negative water budget, which amounts to about 1 meter per year, so the fact that there is more evaporation in the Mediterranean catchment than precipitation, this leads to these higher salinities of 37 to 38 grams per liter. The water flow in the Mediterranean basin is pretty well known today, not just from measures, but also from models. There is a good understanding. But the complexity of this water flow can be summarized with this cartoon here, a sequence that is depicting this inflow of surface, less saline water from the Atlantic, interfering with a lower layer of dense, high salinity and warmer water flowing out of the Mediterranean. And it is this two-way flow across the Strait of Gibraltar here that ensures that the steady state salinity in the Mediterranean side is not going higher than this 37, 38 grams per liter I was mentioning before. That's, of course, an oversimplification. The reality is much more complex than that. And these currents are not uniform through time, but they vary even in a daily time scale. And this is because of tides. So because of the changing tides in the Mediterranean, in the Atlantic side, in the left side of your image, these models, also constrained with data, these models are showing how the inflow towards the right, towards the Mediterranean, and the outflow of this lower layer underneath are interfering with each other. This is beautiful because it provides, it generates this interaction between the inflow and the outflow of the two currents, produce these internal waves that you see here. And these internal waves are actually visible from satellite imaging, like the one you have on the left. And if you are lucky enough, you can even see them from the Gibraltar Strait itself, if the day is very clear. These internal waves are about 100 meters in amplitude at the interface level. And in the surface, they can actually represent some problem for navigation in some cases. Anyway, this mixing that is occurring today in the Gibraltar Strait, this must have been cancelled at some time during the latest Miocene, when these open marine waters and these lake systems in the Parathetis that I was mentioning, they became separated from the Atlantic Ocean. All this widespread salt precipitation happened, and this brackish water in the Parathetis became temporarily also disconnected from the system. And what we know today with a much better precision is the amount of salt that has been accumulated in each of the sub-basins. This is representing mostly halite. You can see that the thicknesses of halite are much more important in the east. And this volume resulting from this compilation of seismic profiles, this is very important because that gives a very good constraint, this 1.8 10 to the 18 kilograms. This gives a good constraint as to what is the minimum time needed for this process to happen. So if you remember what we saw in the what I just showed in the Sicily salt mine, this cyclicity in the salt was suggesting a few tens of thousands of years. And if you take the net evaporation in the Mediterranean today and try to explain this volume I just mentioned of halite accumulated in the Mediterranean, then you go also, you obtain very similar order of magnitude, again, in a few tens of thousands of years. So that should be the time, a minimum estimation of the time needed to evaporate this. The problem is we don't know what is the maximum estimation, because this would be the case for a completely isolated Mediterranean, but probably the initial stages of the Messinian salinity crisis, the Mediterranean Sea was not fully isolated from the west in the Atlantic. All right, so now what can we do with these mechanistic models of erosion? What we did is we coupled laws of erosion along the seaway related to this flow of water from Atlantic to Mediterranean to replace the water evaporated in the Mediterranean basin. And the purpose of this was to see if by coupling a constant tectonic uplift across the Gibraltar Strait, coupling that with the erosion produced by inflowing waters, whether this could sustain a long-lasting initial stage of full or nearly full isolation that allows the salinity in the Mediterranean side to become very high and allow first gypsum and then halite precipitation. The erosion models are based on river incision studies, like this one here, where the measures of incision rates are based on Holocene terrace dating. And if you plot these terraces dating and the incision rates they imply, what you do is you date a river terrace and you divide by the elevation of these terraces above the present river channel. And from that, you get an incision rate. And you plot that against the shield stress of the water flow along the river. And you must assume that the river has kept the same water flow regime since the formation of this river terrace. Then you can have an idea of what is the efficiency of the erosion as a function of the water flow regime along this river channel. From here, you get these erosion laws. There are different versions of that. I don't go into detail, but this is what we have coupled with what happened across the Gibraltar Strait during the crisis. And I showed these two examples where you have this. This is time in the horizontal axis, and these black lines are showing for a seal depth that is forced to go up to uplift and approach the level of the Mediterranean, which is in this different scale here. So when it gets close enough to the sea level, then the amount of water that can flow towards the Atlantic and to replace evaporation is reduced. So the Mediterranean level is lowered, and when lowering, then it increases the energy of the water flow coming from the Atlantic, because the Atlantic will not change in level. The Mediterranean is moving, the Mediterranean surface is moving down. This increases the energy of this flow of water crossing the strait, and this enhances erosion. So eventually, steady state between the uplift of the seaway trying to close the gateway and the erosion capability of this inflowing waters is attained. And what I'm showing with these two examples here, this the fast uplift rate, this light gray, and this slow uplift rate in this dark in black, is how in both cases the equilibrium level reached by the Mediterranean is different. The faster the uplift rate of the sill, the lower the Mediterranean equilibrium level, because the water will need more energy to compensate for the uplift that is trying to close the gateway. But what is important here is that thanks to this mechanism, we could explain why there is a long period, in spite of sea level oscillations in the ocean, or in spite of climatic changes in the Mediterranean. Even if you have a very shallow gateway allowing the water to flow in, erosion is a mechanism that allows you to preserve for a long time period this inflowing water into the basin without completely disconnecting the Mediterranean from the rest of the ocean. So this would be a schematic representation of this process, with the Mediterranean maybe changing slightly through time. And the energy of this flow is what is actually eroding this sill that is trying to uplift, but it cannot cope with, it cannot overcome this erosion power of the inflowing water. What could be the cause for this uplift in the seaway? First, I will show these tomographic results from the area between Iberia and Africa. Look at this location map here. And what this moving cross-section shows is this slab in blue colors. And this slab, as you move towards the east, this slab is becomes broken and detached from the upper plate. The upper plate would be in the left, and it's southern Iberia. This is what we interpreted in this article as the result of a slab tearing and detachment from the upper plate. And as a result of this tearing, we have run these recent models that show that as a result of this tearing, you can explain the uplift of the upper plate in areas where the weight of this downgoing subducted slab is not hanging from the upper part of Iberia. Well, this model, I'm going a bit too fast, but this model is showing the downwards velocity of the subducted slab. So these oranges are showing where the slab is sinking faster. But what matters is actually the topographic response to this model, which is shown here. And what matters is that right after the detachment of the slab happens, then you get this uplift of the left plate, which would correspond to Iberia. And as the tearing propagates, well, north would be on your left side here. As the tearing propagates towards the west, then the topography of this seaway would decrease and eventually would become above sea level, closing the gateways. That's the idea that we have been working on. This is still work. It still is under review right now. So in summary, the general interpretation is more or less what we published in 2011. The idea is that due to this tearing of this subducted slab underneath Iberia, this betic chain and the Gibraltar Strait is undergoing vertical motions, first closing the gateways between Atlantic and the Mediterranean, and then pulling down in the Gibraltar Strait and allowing for the reconnection of the basin. That was the model that we were proposing. This was nicely independently confirmed, the idea of this slab tearing, quite about the same year, and by means of the study of focal mechanisms of earthquakes in the area, below the Betic Cordillera. And these focal mechanisms seem to be consistent with this slab clearing going presently on underneath the Western Betics. Well, this is a movie, an animation explaining a little bit this phenomenon. Okay, this tearing, and I have to move on because then the question remains as to what is controlling the salt accumulation in the deeper areas of the Mediterranean, and what happens in the shallower parts. And this is part of Hanneke Heida's thesis, is still in preparation, but part of it has been already published in Basin Research, and it shows that there is actually not just salt in the deepest parts of the Mediterranean, but also in shallower basins in the Balearic promontory. And this is very interesting because it suggests that precipitation started before or in the earlier stages of sea level drawdown. And why we don't find halite in the shallower parts of the Mediterranean, that's an interesting issue that might be explained by recent work by Lenski and others in the Dead Sea, showing that actually the precipitation of halite is much more controlled by temperature rather than evaporation. And this implies that during drawdown, the water has a high capability of diluting the salt that is precipitated in the margins of the basin. So that would be an efficient mechanism to remove halite that might be precipitated in the marginal areas of the Mediterranean. I need to skip things because we are running out of time, I guess. But these are images from the Dead Sea, eroding, like a perfect analog for what happened in the Mediterranean, the level of the Dead Sea moving down due to anthropogenic reasons, and erosional features in the Nile River and in the Malta Escarpment, suggesting very changing amounts of sea level drawdown in different areas of the Mediterranean. And this is suggesting that each subbasin is behaving independently due to the many seals that are separating the different domains. All right, I will move to the final part of this presentation, just to mention how this story ends. And it ends at the Miocene-Pliocene boundary. It ends very sharply, as I mentioned, and we, based on seismic surveys in the Gibraltar Strait, showing seismic erosion channel connecting the Atlantic to the Mediterranean. This very deep feature of 6 to 800 meters in depth and 10 and more kilometers wide. This is what we interpreted as the result of erosion produced by the inflow of water from the Atlantic, causing a large flood, refilling and putting an end to the Messinian salinity crisis. I don't go into many details, but in this paper, 2020, we have some summary of what are the constraints on this, what the intensity of this flooding that we derive reaches about 100 sverdrups, or 100 million cubic meters per second. And what we did is we estimated recently what is the transport capacity of this large flow of water for each grain size of the sediment, so that we can match this distribution of plastics in the Mediterranean basin and compare with IODP cores. Another hint supporting the idea of this mega flooding is this presence of a very chaotic, transparent sedimentary unit east from the Malta escarpment. This is what we interpreted, this unit 2 is what we interpreted as the result of the transfer of water during the refilling of the Mediterranean, transfer from the western basin into the eastern basin. And there is this, another thing you would expect in such a scenario of a large flow of millions of cubic meters per second is something as what you can see in the Missoula, in the Washington state in the USA, formed by the Missoula floods. This horseshoe-shaped erosion features that resemble very much as this canyon that was found we reported in this article a few years ago, the Noto Canyon, that has this very similar shape. So that could be a hint of where did this water transfer from the west to the east of the Mediterranean. But the most, probably the most interesting or the most solid independent evidence for this is a very recent paper. This has been published only a few weeks ago by Amaratunga, Rowling, and others from Melbourne University. And what they show, based on models constrained by IODP sapropel formation in the west and the eastern basin, is that the formation of sapropels, high organic content deposits in the eastern basin, and the lack of this at the earliest Zanclean time in the west, this seems to be consistent with this sudden and high energy release of water from the Atlantic, first into the western basin and then into the eastern domain. Very interesting paper. I don't have time to. Okay, so that would be a summary of the whole set of mechanisms that I personally envisage as responsible for the events I was talking. And with this, I will finish the presentation. So the idea is that as the mechanism responsible for the isolation of the Mediterranean basin, the main responsible would be tectonic uplift due to a deep slab that is being detached underneath the Baltic system. And this entered in competition for the first stage of the Messinian salinity crisis, entered in competition with the erosion produced by the inflow of Atlantic waters into the Mediterranean. This progressive isolation leads to the gypsum precipitation of the lower unit, the crystalline pure gypsum I showed in the pictures. And only after, when getting close to the full closure, salt precipitation starts in the east basin with very reduced outflow. And the full closure and the drawdown and precipitation happens together once not only the outflow of water, but also the inflow is cancelled in the Gibraltar Arc area. That's the time when this marginal erosion starts, recording mostly in the margins. And then this drawdown stage is continuing and is facilitating the erosional capture of the surrounding basins. Probably the Paratetian is captured at that time, and that would explain why you have this sudden appearance of Paratetian species in the Mediterranean record. And finally, the sinking of this slab underneath the Gibraltar Strait leads to allowing the Atlantic waters to enter the basin. And because of the erosion feedback with the amount of water that can enter the basin, this flooding becomes very accelerated, and it changes, it puts an end to the Messinian salinity crisis in just a few years, probably. So this is it, 谢谢, and I think that's all I can say in Chinese, and I will leave you with this other video as an animation by the University of Malta that is kind of summarizing the entire mechanisms. And I just leave it open for questions if you have any.